Good morning, good afternoon, and good evening to everyone joining us from around the world. Welcome to the second advancement in atmospheric water harvesting hosted by International Atmospheric Water Harvesting Association, together with the Arizona State University and Northumbria University. My name is Amin Mojiri, and it is a pleasure to serve you as a moderator today. Our goal is to discuss the future of atmospheric water harvesting, share new ideas, and build collaboration that can help create sustainable water solutions for community across the world. Before starting the presentations today, I would like to invite Professor Paul Westerhoff to officially open the webinar. Professor Paul Westerhoff is a Regent Professor at Arizona State University, a globally recognized leader in water technology, and Director of the Global Center for Water Technology. He has published more than 500 journals papers, received many national and international awards, and was elected to the National Academy of Engineering. He is also served as the president of the International Atmospheric Water Harvesting Association. Professor Paul, thank you for joining us, and the floor is yours.
Great. Thank you, Armin, and welcome everyone. I'm going to go ahead and share a few introductory slides here. Um, so Armin asked me to talk for about 10 minutes to kind of open things up. So first, welcome to this seminar. And, I know you all know about atmospheric water harvesting, but during this little welcome event, I want us to kind of think about a challenge that is the same challenge I gave to an online webinar in China that had over 10,000 people again earlier in September. And that is a challenge that we should figure out as a community how to produce over 1 billion cubic meters of atmospheric water per year. So most of the stakeholders I talk to, whether they're end users or manufacturers or regulators, or people who want to think about the availability of water, really only get serious about investing in water when the size of a market is on the order of 1 billion cubic meters of water annually across the globe. Other people think about how much money is invested in a sector, but for I think water, this is important. And I think it's played out in other clean tech, namely thinking about solar. The growth of the solar industry was really fairly small until it posed and approached and then exceeded a terawatt of installed solar power globally. So this type of focus really helps focus research, applied development, end users, and investment by communities because they see a community that's organized, they could understand supply chains and markets, and people don't have to keep explaining why should I use your technology. So 1 billion cubic meters is not really that much water. It's 400,000 Olympic swimming pools. That sounds like a lot. But if you look at Intel and their water conservation goals, it's zero point 0.2 billion cubic meters by 2030. So this is a large number, but on an order of magnitude of what gets large corporate companies interested in technologies. So again, going back to this idea of a terawatt challenge, they could map out across the globe the cumulative capacity. And you see, we somewhere in the last few years just passed a terawatt of installed solar energy globally. And so this types of things help understand why technologies can emerge. So how much atmospheric water do we already harvest? If we want to get 1 billion cubic meters, it's hard to understand. But if we look at some analogous things that we're already doing, like air conditioning, and just look at how much condensate we are producing in Phoenix, Arizona, which is a state or a region that has about 30% relative humidity, one building collects about 500 cubic meters of condensate per year. And so if we just looked at across the United States and assumed there was no wetter or drier relative humidity than Arizona, it's about 500 million cubic meters of condensate is already being produced. So we're taking this amount of water out of the air, and we're not fundamentally changing the ecosystem around us, but we're not using this water to its highest beneficial use yet. So I think a billion cubic meters of water is kind of achievable. Now, of course, we have to do that at an energy consumption and water quality that is also reasonable for end users. So that was the message I wanted to try to get across here today. I'd have just kind of 2 more slides to think about that. So I think I stopped sharing accidentally there, sorry. So the question is, how do we get there as a community? Well, we can look at other clean tech, other water tech. This isn't solar, but now this is reverse osmosis. And kind of the growth of reverse osmosis installed capacity, millions of cubic meters per year. So they're not at 1 billion cubic meters of installed capacity yet, but in the blue bars, you can see the growth they soon will be at over 1 billion cubic meters of installed capacity around the world. But sorry, they already are, because this is 1 million cubic meters per day. Now, the milestones along here map out some of the key innovations that unleashed this exponential growth. It wasn't the first patent in 1981. It wasn't the first device that made it to the market. It really was a material innovation, a thin film composite membrane, and an energy recovery and membrane resistant fouling that led to this exponential growth. So we sketched on this line. Hopefully, we're faster than this, but there's some innovation period going on in atmospheric water harvesting today, and at some point we'll have this exponential growth. So I think tracking this type of thing, many fields in the clean tech do this to understand where they're going and how innovations are advancing the field. So to do that, again, I think we need a systems innovation and a material innovation. And we made up this plot of the number of publications. Again, not the same metric, but it's looking at materials, systems, and other publications. So you see a lot of work on material innovations. Great work on MOFs. Omar Yaghi and 2 colleagues, won a Nobel Prize in Chemistry this year for discovery of MOFs, which are in part used for atmospheric water harvesting. But that little yellow bar is the systems innovation. There just aren't enough papers being published, I think, that look at technoeconomics, thermodynamics, and this system integration of fans with devices and trying to understand how to keep getting more and more efficient systems. So I think, as we look forward, while small systems are useful, a small solar panel, think about the terawatt challenge, a relatively small atmospheric water harvesting system, think about 1 billion gallons a day. But if we're going to get 1 billion cubic meters a year installed, it's going to look more like the thing here on the right-hand side rather than the left-hand side. And you can still find people using solar panels like the left-hand side, but it's cheap because of things like the right-hand side. So I guess my goal of thinking here today is we should think bigger, we should be bolder, and really help push this industry forward to achieve all the things that each of us want to do around clean water. So with that, thanks, Amin, and I'll hand it back to you.
Thank you very much, Professor Paul, for your opening. Before go further, I would like to share some slides about Atmospheric Water Harvesting Association. Okay, International Atmospheric Water Harvesting Association is a global non-profit network supporting innovation in atmospheric water harvesting. We connect researchers, industry leaders, and policymakers. We organize international webinar conferences and training programs, providing open access resource for AWH communities. Please join us for free of charge with scanning this QR code. And please subscribe to our YouTube channel. We publish technical talks on atmospheric water harvesting, research highlights, expert interviews, webinar recording, and educational videos. Also later, this webinar will be shared on our YouTube channel. Please subscribe with scan this QR code.
But we took this picture, and we'll take another picture soon. This was our second atmospheric water harvesting summit. And our next one in Arizona is in about 2 months in January. So we welcome everyone to come. We're going to have, we're not going to record the whole thing, but we're going to do some interviews while folks are there. But again, in the spirit of QR codes with Amin, go ahead and scan it. And, we welcome you to come. But the reason we're doing this and events around the world is not everyone can travel halfway around the world. So once again, thanks and welcome. And I'll hand it to Amin to introduce our speakers. Thanks, Amin.
Thank you, Professor. Okay, our next speaker is Dr. Lucia Cattani, R&D manager at CISA and an internationally recognized expert in atmospheric water harvesting, building energy integration. She has contributed to major innovations in AWH technology and water energy system. Her talk today is titled Smart Water from Air, Integrating AWH into Building Energy Design. Dr. Cattani?
Here I am. Thank you, Professor Amin. I'm here. I'm going to share the video. Okay. Can you see the video? Oh.
Yes, perfect and clear.
Perfect. Okay. Thank you so much for your kind presentation. I am also adjunct professor of environmental impact energy systems in the University of Pavia, and I'm very glad to be here today to speak about atmospheric water in this important webinar. As we know, water and energy are strongly related one to another because we need water to provide energy and vice versa. Such a link is even stronger when we speak about atmospheric water, and we know that even passive systems need some kind of water. And we know that we must address water energy nexus by an integrated approach, not only at national infrastructure, but also at urban scale. Building design solutions should address the water and energy issues at the same time. In particular, we must remember that buildings account for about 1/3 of the total energy consumption, and such a consumption should be decreased if we wanted to address the global warming, if we want to counteract the global warming. Therefore, we must improve the efficiency of the buildings and their HVAC systems. On the side of the water issue, we must remember that water crisis affects the availability of water, not only at global scale, but also at urban scale. Therefore, increasing the resilience of building is important, and atmospheric water can play an important role in such a resilience augmentation. But as we said before, atmospheric water needs energy. Therefore, we must be able to afford the water energy nexus also for atmospheric water harvesting. Therefore, multi-purpose engine, multi-purpose equipment, which are able to provide more than one useful effort with the same energy consumption can be the answer. We can improve at the same time the energy efficiency and provide water at the building scale. We know that CS is a leader in this sector, and we know also that research is focusing on such a multi-purpose machines, which can be the game changer. But if we want that atmospheric water gain its due position among the water resources, as underlined by Prof. Westerhoff, designers must be able to put inside their project such a kind of solution. So we must provide them with tools that permit them to put inside the building projects such a kind of AVG, atmospheric water generators, which are able to provide atmospheric water and energy efficiency. How we can do that? First of all, we studied and we formulated indexes and indicators, which are very important at the first stage of the design project, when the designer have to decide which kind of piece of equipment put inside the project, and the judgment is based on the efficiency. I can remember to do the Advanced Global Efficiency Index, which is an index that is able to provide by a single number the overall efficiency of a system configuration, a complex system configuration, which can encompass not only heating, ventilation, and air conditioning, but also water harvesting. In such a way, we are making possible for designers to choose also atmospheric water generators for the building system configuration. But when in-depth energy analysis are required, for example, energy audits or certifications, dynamic simulation tools are typically needed and employed. Therefore, also to addressing the water energy nexus, we must have a dynamic perspective. By this perspective, we decided to try to link two dynamic simulation tools in order to provide, as I said before, designers with project tools, as I said before, to address the energy and water issue at the same time. The first dynamic tool is Energy Plus, is a design builder, which implements Energy Plus. We know that Energy Plus is a powerful simulation engine for modeling building energy performance. And the idea was to be able to import the energy behavior of a multi-purpose AVG machine inside such a kind of simulation tools. In order to do that, we used also AVG Sim, which is a tailored dynamic software which implements energy and mass conservation principles, which can calculate both the transit and steady state behavior of the machine, providing a real-time simulation of the behavior of the AVG, not only in water making, but also for the potentialities of cooling and heating. I must remember that such a kind of machine are based on the compressor reverse cycle and are able, with the same energy input, to provide not only water harvesting, but also a cooling and a heating power, which can help the existing system or a new system of a building. We used such a kind of simulation tool, the AVG Sim, on real-life machines, such as the AWA 250 produced by CS, and we obtained optimal results in terms of the mean absolute error, which is less than 5%. As a first step of our research, we tried to connect the two simulation tools for a simple building. In order, and in this case, the atmospheric water generators multipurpose was able to provide water and cooling for a simple building, housing inverter and transformers intended for a photovoltaic system, which was the scopus of a previous research. Such a photovoltaic system was intended for hydrogen production, green hydrogen production. But this building, housing the inverter and the transformers, needed cooling. Therefore, we said, okay, the AVG will produce water, but also the cooling needed for the building. And we want to have a tool in order to make the simulation of the entire building encompassing the cooling given by the AVG machine. We wanted to have such a tool in order to make simulation for various, for example, climates and so on, various temperature and humidity situations. Therefore, we imported inside Design Builder the building by means of real-life data. And after that, we imported the AVG machine inside the Design Builder, the cooling behavior of the AVG machine by means of the results given by AVG Sim and library components, standard library components existing in Design Builder, properly sized and scheduled in order to represent in duly way the AVG behavior. And the results were very satisfactory because the error between the two simulations was very, very, very low, below the 3%. After that, we carried out the simulations and we find out that, for example, in Hariomote climate, which was the climate of the previous research, the help of the multipurpose AVG was important because gave an energy saving of about 30 megawatt hour a year. After that, we made a further step, expanding the method for a very complex building and including inside the B, we tried to include inside the B, all the energy functionalities of the AVG. We chose the hospital Mondino in Pavia, which is nearby the University of Engineering of Pavia. And as you can see, the geometry is enough complicated, as well as the fabric of walls and roofs and so on, and also its system. We imported inside Design Builder the model of the hospital by means of real-life data, and we test the existing building with its system against real data energy consumption. And as you can see, we obtained very good agreement. After that, we imported inside Design Builder the behavior of the multipurpose AVG by means of AVG Sim, and as before, by means of a standard library component and proper scheduling and sizing. But this time it was a little bit more complicated because in this case we wanted to connect all the existing system with the energy supplies given by the machine, all the fluxes provided by the machine. Therefore, the effort was a little bit more strong. You can find the details in the published papers. We obtained very good results in terms of reliability of the models. And after that, we provided other simulations of the behavior of the machine. And we found out that during the drought-prone period of the climate of Pavia, which goes from May to September typically, the machine can, the AVG, the multipurpose AVG machine, can not only give an important help for the efficiency of the existing plant. The help can go from 16% up to 56% of energy saving. But After that, the machine can provide more than 255 cubic meters of drinking water, contributing to resilience in such a crucial sector as an hospital. We must remember that atmospheric water is a noble water source because it can be produced in locations where no other sources are available. However, as we said before, it requires energies, and the quantities that can be obtained are somewhat limited. Therefore, we must carefully choose the employment of such noble water, of course, for human consumption, which is a very important final use of such water, but also for strategic crops, hydrogen production, technical, industrial scopes, and healthcare applications. But if we wanted to use the water for such strategic fields, we must assure that the quality is granted. Therefore, we must remember that atmospheric water is not pollution-free. It is less polluted in comparison to other sources, in particular lakes, rivers, forest aquifer, and so on. Nevertheless, there are some pollution which must be avoided or removed For example, air should be filtered if you want to avoid airborne particulates and animal digestion, insects, and so on. Biological proliferation should be avoided by means of disinfection systems. We must avoid that the system used for atmospheric water harvesting becomes itself a source of pollution. Therefore, all the components which come into contact with the condensate should be certified for food and beverage contact. And we must remember that there are some water-soluble air pollutants, nitrates, ammonia, some alcohols. In particular, we must remember that there are many countries which have a limit of 0.5 milligram per liter for the drinking water of ammonia, and ammonia is an important water-soluble air pollutant that we find inside the system. Therefore, we must remember to remove it. Finally, we must remember that if we treat outside air, we find less pollution in comparison to treating indoor air, inhabited indoor air, underlined by Anna Jurga, Chao Zheng, and Professor Westerhoff. It is important to remember that. Up to date, we are working in Pavia on our 25 by CS, which is a machine studied to provide drinking water because it has a filtration, a due water treatment unit, material certificated for food and beverage grade, and so on. But we are going on with the research, and we are trying to understand the suitability of the produced water for advanced uses, for the hospital application, in particular for laboratory use. You must know that the water used for the laboratory is very costly because it must be high pure. And in many places affected by drought, hospitals must buy such water from other regions, paying a lot of money. If we are able to provide a noble source as atmospheric water of the due quality, we can understand that we can be game changer in the cost management of the hospital regarding the laboratory use. After that, we are also studying, defining an indicator for the water quality index. There is a recent research that tried a first indicator, but we wanted to focus on the typical pollutants of atmospheric water. We wanted to focus the attention on that and to formulate an index that takes into account such a kind of solution. And after that, we want also to take into account the energy required in order to achieve the wanted quality. Therefore, which are the future developments of the research? I must say that we carried out we have two branches, we can say. One is providing the tool for designers in order to let them to include inside their project in the buildings of atmospheric water generators, and in particular for the multipurpose one. This is one branch, and we are working on it, refining the method, simplifying it, and carrying out simulation in different places of the hospital and so on. We also analyzed other archetypal buildings, and results will be summarized in a poster for the 3rd International Summit of Genoa. On the other side, we are working on the quality of water, because we must remember that the quality is one of the most important things of atmospheric water. Therefore, we are analyzing from an economic point of view the importance of giving high purity water, and on the other side, we are working on the appropriate water quality indicator, which takes into account the atmospheric water pollution and the energy required in order to obtain it. Thank you for your kind attention.
Thank you, Dr. Cattani. If you have any question, please raise your hand. I will unmute you and you can ask, or you can simply write in the chat.
I have one.
Yeah,
I do have one, Amin, and while other people are typing there. So really enjoyed the presentation. Glad you're going to be coming to our summit. So within this hospital application, you talked about the technology, but who have you convinced to use the water, and what questions, if you did convince them already, what were their questions that you had to answer before they were willing to use this water?
In this case, as I said before, dear professor, we carried out a simulation of the use of the machine inside the hospital, because this part of the research concerned giving designer a tool in order to insert inside their project something that can encompass also our water harvesting, because we wanted to push such a technology, because we researchers know the importance of atmospheric water in water resilience, in enhancing the system and so on. But if designers do not have designing tools, cannot do that. On the other side, to convince people to drink water is another question, but it is not difficult in our experience, where we experienced that in other places, not in the hospital, in other occasions, because normally our water, the water produced by this system, is very good. It's very tasty. Normally we use it. You know that in Italy, we have the certification.
Maybe it was the slide below for that AW25. What are they actually using the water for? Are they using the water currently for something?
Inside the hospital?
Yeah.
The water in general. As I said you before, in this hospital, we did not connect the machine, the real life machine, but we provided a simulation. The uses of water inside the hospital are very, very different. It goes from the drinking water to the water used in laboratory, and so on. Therefore, there are different qualities of water. I can say to you an important thing. In Italy, we have got a law that it is that comes from the European indications, which assess that the water is drinking if it is in compliance with the limits, and even if you are taking it from sources which are not traditional. Therefore, it is not difficult to provide water by means of atmospheric water generator. In Italy, it is accepted. It is accepted because you have only to demonstrate the right thing. The quality is in agreement with the laws. Up to date, there are moments of drought, and during also in the northern part of Italy, not only in the south where the Isha is a very strong Isha all over the year, but also in the northern part of Italy. And during such a period, you have no water. You have no water for purposes which are not drinking purposes. For example, you cannot provide the cleaning of a photovoltaic system. You cannot water crops and so on. Therefore, such a kind of solution is a game changer for noble scopes. Not to wash, for example, the floor or to clean the floor. No, I will not give my water to do that. But if you want to employ it for noble scopes, our water is available.
Okay, thank you, Dr. Cattani. May you please stop sharing?
Yes.
Okay, thank you.
Right.
Thank you. Our next presenter is Professor Hafiz Muhammad Ali from King Fahd University of Petroleum and Minerals. He is an expert in thermal engineering, radiative cooling, and sustainable energy systems. With more than 400 publications and international awards, Professor Ali will speak about radiative cooling and its role in air water harvesting.
Thank you very much for inviting me to present some of our work for radiative cooling. So today the title of my talk is radiative cooling and its role in air water harvesting. Myself is Hafiz Muhammad Ali. I'm working as a distinguished associate professor of mechanical engineering at King Fahd University of Petroleum and Minerals in Saudi Arabia. So today my presentation, it will be covering some of the introduction into radiative cooling. We will be having some recent advances. I will be presenting that. After that, we will see that what are our contributions into radiative cooling and specifically into air water harvesting. And finally, we will be going to the conclusions. So we know that depending on the wavelength, we can have different types of rays, gamma rays, X-rays, ultraviolet, or more appropriately for maybe mechanical engineers, we have thermal radiations, which will be having visible radiations and infrared spectra. So now we know that if we talk about atmosphere, so most of the visible radiations, they are basically atmosphere is transparent for them and they can reach to any surface. But when we have some infrared radiations getting out of a surface, so this atmosphere becomes opaque and most of the radiations becomes blocked. But somehow, if we have materials that are able to radiate within a specific window, that radiations directly go to the outer space, which is generally at 3 Kelvin. So we can have something which is called radiative cooling. So ultimately here you see that a radiated cooler surface, then it will be receiving sun radiations and radiation exchange with the atmosphere. Then we have some radiation exchange with the outer space and convection and conduction heat transfer to the surrounding, or maybe if surface is touching to the other materials. So here you see that especially, the solar spectra, most of the radiations, we know that the emissivities, we know about them, they can cross the atmosphere and can reach to the earth. But when we talk about the black body radiation spectra, especially at 300 K, which is about atmospheric temperature, then the transmissivity of black body radiation, this is good enough and it is up to almost 100%. And atmospheric transmission window, if we talk about in between 8 to 13. So this is atmospheric transparency window. which will be ultimately allowing these radiation to leave the space, and it will be providing radiative cooling. So this radiative cooling, then of course, this is dependent on like the selective emissivity of the surface of within the atmospheric transparency window, and what is the view factor of the surface. So based upon that, then a lot of work which was started right in 1967, some theoretical proposal about radiative cooling during daytime. And in 1975, some early experimental demonstration was made during the nighttime radiative cooling. In 1977, some practical nighttime cooling system was developed. And then after a certain gap in 2014, a landmark daytime cooling breakthrough was done by subambient cooling under direct sunlight by A.P. Raman. And in 2017, some scalable coating and radiative cooling materials were introduced. In 2022, we had some radiative cooling paints. So now the radiative cooling, then in this perspective, it might be now used in several different applications. So we are specifically, looking into the application for air water harvesting. So what are different materials that are used or that can be used for the radiative cooling? So they depend on like homogeneous materials, composites, dynamic or multifunctional material. But some key categories for radiative cooling materials are nanoparticle embedded polymers, porous materials, hybrid metamaterials, fluorescent pigment coatings, shielding materials or multi-layer photonic structures, etc. Some of the materials, for example, barium sulfate nanoparticle films and paints have been used in literature, and we were able to achieve radiative cooling in under direct sunlight and with a temperature, subambient temperature 4.5 degrees C. And graded nanocomposite metamaterials, they were able to produce radiative cooling up to subambient temperature 14 degrees C. Then PDMS with a combination of metal thin film, they have ability to produce radiative cooling during daytime, subambient temperature up to 11 degrees C, and with a cooling power of up to 120 watt per meter square. Then there are some other materials like porous polyethylene films. These materials are good enough and they have a good emissivity, mid-infrared emissivity, and for achieving some kind of subambient cooling of 5 degrees C. And most of the solar radiations that are falling on these kind of materials, they will be almost mostly, they will be reflected. So here you see that some different structures with different materials. We can see that what is the average emittance in atmospheric transparency window. So you see that like PDMS, they are going to have very high emittance within the atmospheric transparency window. And here you see that the solar absorptance of these materials, this is extremely low. So they are good materials that can be used for radiative cooling. And some of the shielding materials, as we already talked about, the polyethylene. So here you see that the solar absorptance is really low, but the transmittance in atmospheric transmittancy window, this is really high. Okay, so what are the models available, that can be used to have some power estimation for the radiative cooling surface at ambient temperature? So this is a simple, the cooling power that we may have on a radiative cooling surface, which is dependent on the radiative cooling with the atmosphere and the communication with the atmosphere. The material is going to receive some of the radiations from the atmosphere and radiations from the sun, and ultimately the conduction and convection heat transfer. So if this radiative cooling is going to overcome all of these other kinds of heat transfer. So ultimately, we will be having that cooling. Looking into then the model that we use then for passive condensation. So that the cooling could be provided by the radiative cooling or maybe some positive convection on the top of the surface. At the same time, the surface is going to be heated with the solar irradiance or some of the atmospheric radiation heat transfer. But ultimately, some of these two would be positive on the surface. So on the other end, where the air is going to touch to the cold surface, if that cold surface reaches to the dew point temperature, so we will be having sensible and latent heat transfer there. So ultimately, the water condensation can be achieved on this part. So the same concept of radiative cooling, this is also sometime important solar sails. So there are some of the assumptions that has been given in the literature. For example, the solar absorber absorbs all type of solar radiations within a limited depth. The condenser is optically transparent to solar radiation. The solar still is perfectly encapsulated against all type of vapor losses. And this analysis basically is done in equilibrium when we do these calculations. So looking into the details that what are the total, heat transfer, it will be dependent on the solar radiation absorbed by the absorber. Then what is the evaporative heat flux, plus the convective heat flux, plus radiative heat flux, and finally the heat flux from absorber to the bulk water. But on the condenser side, we will be then looking at into the convective and conduction heat flux from the condenser to the environment, and then finally the radiative heat flux from condenser to sky. So if this balance is achieved, so ultimately the water harvesting within the solar panel, solar stills, it will be achieved. What are the important applications of the radiative cooling? So it can be used to provide cooling to the photovoltaics and the buildings with some kind of paints, urban heat island, and personal thermal management. We may have different types of fabrics, and into the power plant condensers to reduce the temperature, condensate temperature, and to have more heat transfer, and some vehicles and greenhouse. So looking into, into these fields, we do have a lot of literature available, especially for photovoltaic, where we have seen that the sub-ambient temperature can be achieved up to 5 degrees C. And once we look into buildings, so different types of paints are now have been researched and reported, which can achieve temperature reduction up to 9 degrees C or more than that. Similarly, urban heat island work is available there. For personal thermal management, there are variable radiative cooling fabrics that can achieve temperature with the skin, and a sub-skin temperature may be 5 to 6 degrees C under direct sunlight. It can be achieved, which will be ultimately providing cooling. And within the power plants, some of the application of the radiative cooling has been reported. And for example, by providing radiative cooling coatings to condensers, that increased rejection of heat by 12%, lowering condensate temperature by 5 degrees C, and so on. Similarly, in vehicles and greenhouse, these kind of radiative cooling films, by optimizing the geometry, they can reduce the temperature up to 9 degrees C. But here we are more interested to look into that how we can achieve condensation, because we are interested into the air water harvesting. So some of the work that has been reported for the solar panels. So this work basically reported in 2020. The objective of the work just to provide condensation to have some kind of dust cleaning of solar panels. So utilize panels during night, which was able to get atmospheric air water harvesting, and then they achieved up to 261 milliliter per meter square per week of water generation, was sufficient to clean the dust for solar panels. Then another application has been reported to collect some of the water. And here you can see that radiative shield and cooling for heat dissipation to the outer space. This was combined together. A super hydrophobic condensate harvester was made on the below part, and it ultimately achieved dew point and a collection of water up to 50 grams per meter square per hour was reported. And here you see that the selective emitter was placed with the PDMS and chromium, silver, and chromium 1 nanometer thickness again. So looking into that, during like when the relative humidity is more than 90%, so during daytime they achieved dew, and even when the relative humidity was low, up to 65%, still we can see that the dew is still there. And some of the tests reported at on 30th August, we can see that the water collection was up to 50 grams per meter square per hour. Okay, so what are our contribution into the air water harvesting? So we made some of the emitter. So the emitter preparation was with the help of 0.5 millimeter thick polished aluminium as a substrate and used coating material PDMS. And why we use PDMS? Because it has high emissivity in mid-infrared range, which is 8 to 13 micrometer atmospheric window. And this was prepared by using PDMS with curing agent into 10:1 weight ratio. And the curing process was once we had coating over the aluminum surface, we cured at 100 degrees C for 30 minutes. Ultimately, the PDMS layer thickness was up to 120 micrometer. So the double-sided version where we had both sides coated with PDMS and cured under same condition, each was having the coating 120 micrometer. So this is how we create that coating. So this is a mixture of PDMS with curing agent, and by this coater we may achieve this coating as shown in the video. So if we have, what is the ideal emissive power? It depends on the temperature. So for example, if we have ambient temperature around 30 degrees C, so the maximum emissive power that we can achieve is up to 120 watt per meter square. So if we have double-sided coating, this could be then double power up to 240 watt per meter square we may achieve. And when we compare the emissivity of PDMS with ideal emitter, so you see that within the atmospheric window, which is from 8 to 13, so the emissivity is actually near to the ideal emitter. So the reflectance of the aluminium mirror that we used, this was very high, reaching up to 0.9. Some of my work that we have done with our team on the atmospheric air water harvesting, I would like to present it here. So we used a double coated emitter. In this case, one side, it was covered with the polyethylene so that we may have no convection on that side. So the impact of radiative cooling can only be seen. So this is a mirror, which is aluminum mirror. On the other side, which also has a combination of PDMS, aluminium, and then silicone oil. It will also be providing cooling, but at the same time, when water was touching to that surface, it was going to condense, and we had then water collection. So we did some outdoor testing on a smaller sample, which was 13 to 30 centimeters square. And we were able to achieve 21 gram per meter per hour water collection, and that can go for the case of super hydrophobic surfaces. If we compare the silicone oil with the super hydrophobic surface, this is almost double what has been reported in the literature. We also went for indoor tests. So the maximum condensation that was achieved, it was almost 8 to 90%. Comparing to the condensation that already. So here you see that a test was done on 23rd April 2024. So figure A and B, they are going to show some of the outdoor conditions, for example, the ambient temperature, dew point temperature, and we compare that with atmospheric, super hydrophobic surface and also the lubricated surface. So in figure C and E, we can see that once we have lubricated surface, so the gravitational shedding, this was really useful and we were able to collect a lot of water. But when we had some super hydrophobic surfaces, so the droplets were, leaving the surface once they are going to go together with self-jumping droplet, it was observed. So here you see that the testing was also done in indoor where we produced the sky effect by using liquid nitrogen. So here we were interested to see that what would be the impact of different coatings. For example, if we only have PDMS or we have super hydrophobic surface, or finally we have lubricated surface. So PDMS and super hydrophobic surfaces, they were able to collect, there was condensation observed, but the collection rate was very small. But once we have lubricated oil, so there was total condensation and collection rate was almost near to the, what was the total condensation on the surface. So you can see here that we reached up to almost 50 gram per meter square per hour. I would like to show some of the videos here for outdoor testing, especially when we had super hydrophobic surface and the lubricated surface. So we can see that once we have lubricated surface, so the gravity driven condensate movement was really high, that really provided condensation collection. So what about indoor testing on the super hydrophobic surface and lubricated surface? So you see that on the super hydrophobic surface, condensation is there, but droplets are generally there. But once they get together, we will be having jumping of droplets. But on the lubricated surface, gravity, this is basically dominating, and all of the water droplets, they are getting together and moving down. Then what is the conclusion on the work? The passive radiative cooling enables sub-ambient temperature without external energy. Atmospheric transparency window, which is the key parameter, and it should be in between 8 to 13 micrometer to have radiative heat loss. Major progress in material and design, for example, barium sulfate paints are there, PDMS films are there, and nanophotonic structures are there that now can be used in order to get radiative cooling and the use of them into the air water harvesting. So the work we did, it showed that lubricated PDMS-based double-sided condensers were able to eliminate droplet pinning, enables gravity-driven water removal, and it also achieved 87% theoretical condensation limit, which was almost double than the collection rate. So it demonstrates dual functionality. For example, we can get cooling, which is being nowadays used for building coolings, plus atmospheric water harvesting. So the future focus should be on the scalable fabrication, the system integration with some active technology, and that could be done on the all-weather operations. So thank you very much. This was some of my work, and I'm more than happy to answer your questions. Thank you.
Thank you, Dr. Hafiz. If you have any question, please just raise your hand. I will unmute you, or you can put in the chat. You have already 2 questions in the chat. Can you show the urban heat island application again, please? And they want to see also the slide 26.
So this is, some of the data that we have collected from the literature. Here you can see that they developed glass polymer hybrid radiative cooling films with some ambient cooling more than 8 degrees C, demonstrated mass manufacturing via roll-to-roll process for urban surfaces. Some other works, they proposed city-wide radiative cooling panel deployment strategy, achieving surface temperature drop up to 7 degrees C. And some other works introduced low-cost radiative cooling paints using hollow glass bubbles, achieving almost 6 degrees C delta T, which was almost 20% increase in durability versus conventional white paints. So this is some of the literature that we have collected, but our focus was on the air water harvesting. I mean, in terms of urban heat island, we didn't perform any work. This is just some literature collection just to give an idea that what are different applications, for example, into photovoltaics buildings. But our focus that what we are working on the air water harvesting.
Thank you.
Yes.
And Nancia asked, what do you estimate you can produce at lower humidity, less than 65%?
Yes, actually, the radiative cooling for air water harvesting, this is a really challenging field because humidity, this is one of the important parameter, as we know. But other than the humidity, the most important parameter is that how we are going to avoid, for example, the thermal mass that is there around. And if we are going to have high humidity, then it is actually a resistance to the radiation. And even the radiation within, where we have emissivity within the atmospheric window, once the humidity in the atmosphere, it goes high, so it will be ultimately entrapping all of the radiations. So having a low relative humidity, maybe this can promote basically air water harvesting. Okay, so the key things that we need to focus on, we need to see that how can we basically avoid the mass. So for example, let me show you some of my slides here. For example, here you see that we have polyethylene film here. So why we are going to have here, so that we don't have any convection heat transfer, because if there is going to be the convection, so it might be increasing the temperature of the aluminium, and we might not be able to achieve air water harvesting on the other end. So that is why. And the total system, you see that we have styrofoam in order to insulate the system from the surrounding. So if the ambient temperatures are already low, so this is going to help to increase the radiative air water harvesting. But if the ambient temperature is really high, which is generally in the Middle Eastern countries, mostly during the summertime, the temperature is really high, so it becomes really challenging to isolate the system from the thermal mass. So if we can do that, then more air water harvesting can be achieved. I hope that this answers the question.
Thank you. And we just have one more question here. How much of water do you produce at a medium RH, around 60%? In a day, and what is the estimate cost of the cubic metric produced water according to your research?
Okay, right. I think this is a very good question. So here you see that we have one test that we have done around where the relative humidity was over 80%. Okay, so here the water collection during the outdoor, as we have shown that we were able to collect almost 21 gram per meter square per hour. Okay, so we have done some of the tests which are indoor tests. So the relative humidity was changed here. So these tests which are shown here, they are almost inside indoor conditions where the relative humidity was almost 50 to 60%. So even at that relative humidity, the collection rate was really high. As you can see here, that collection rate, when we have lubricated surface, it went up to 50 gram per meter square per hour. So now looking into the cost analysis, which we have already done. So the whole system, this is not very expensive because what we are just needing, we need aluminum sheets and we need some of the materials like PDMS coatings, and that's it. So all these materials are really cheap. But now the issue with the radiative cooling is that this is basically a passive technique. So once we compare this technique with the other active methods for, I mean, water harvesting, it cannot compete. So maybe this could be useful for those places, you know, which are remote places. We might not have any access to the active mechanisms to get the water harvesting, or maybe it could be used in combination, or maybe, you know, once we will be using in combination with some active plus passive, so this gonna increase the system efficiency up to maybe certain percentages. But still, you know, I think the work will, including our experimentation, it has to be, you know, we need to add a lot of more experimental work, maybe at different parts of the world. Okay, so maybe during the whole years, just to see the full potential, and then finally we will be able to estimate that what's going to be the average cost comparing to the active systems. Thank you.
Thank you, Professor Hafiz.